Okay, this is part 2 of the AS Core Paper 1 from Edexcel Linear, June 2024. In part 1, I went through the multiple choice and the first few of the structured questions. So I'm going to go through the rest of the paper, hopefully in one video. Okay, so if you haven't watched the first part, it'll be in the same playlist. Go back and watch that first if you want to. Don't forget to share it with anyone who you know is doing the linear. I'm recently moved back to teaching the linear, so I'm starting to load up more linear videos. So your support is greatly appreciated because most of the people on this channel are used to preparing for the international A level. So AS Core Paper 2 is mainly waves and materials, but the last two questions, as you'll see, could be on anything from the Year 12 content. Okay, so let's get straight into it. You can see that this question is about Stokes' law. Okay, so Stokes' law, mathematically, I've written it out. It'll be in your data sheet. Yeah, which is basically viscous drag. Okay, so state two conditions that determine whether Stokes' law applies to a moving object. So the R in the equation is to show that it's spherical. Okay, so R is the radius of a sphere in the equation above. So 1 mark for saying it's spherical, and it has to be small enough to ensure it moves slowly enough as well to make sure that the flow is not turbulent, that it's laminar. So once turbulence happens, the equation doesn't really work. So you want it to be spherical. You can only estimate, remember physics A level is simplification of reality. If it's any other shape, the equation is not valid. Okay? So, but it's a good approximation of, it's a good way of working out roughly how much drag there is due to a fluid. Okay? Part B, it's got an asterisk by it, so that means it should be a 6-mark question. Yeah, and here are my notes on it. A teacher demonstrated the viscosity of fluids using a falling ball method. That's one of the core practicals, both in international A level and in Edexcel Linear. The teacher released a ball bearing at the surface of a tall column of a viscous fluid. It's tall, so it has long enough to be able to travel through it and reach terminal velocity. The teacher repeated the demonstration using an identical ball, identical ball bearing, I should say, falling through a liquid with a higher viscosity. Okay, so exactly the same radius, just N2 will be greater than N1, or N eta 2 will be greater than eta 1. Explain the motion, of the two ball bearings as they fell. That means you've got to discuss the motion of both of them and then explain the difference. That's what they need you to do. They don't want you to explain the difference. They want you to explain the motion. Yeah, so they're both going to have similar motion. So R is the same for both. Remember that? So that's just some notes. And if N2 is greater than N1, then looking at the equation right at the top of the page, then the velocity will be greater in 1 than 2. Okay? So if the viscosity in 1 is less, then it will be able to go faster. Make sense? So the viscosity is what determines how fast you can go through something. Okay? Imagine trying to swim through treacle, for example. So V1 will be greater than V2 for terminal velocity. So here's my notes. But in both cases, explain the motion. The weight is the same in both. Okay? Initially, the ball accelerates because the weight is pulling it down. So you've got to say downwards. So initially, the weight is greater than the upthrust. So the weight is greater than all the opposing forces because it hasn't built up any speed yet when it first starts falling. As the ball speeds up, however, then you also get the viscous drag increasing, F equals 6 pi r eta v. So then you have the upthrust and the drag, and then the drag force will be greater, obviously, at the speed that it's going at in a liquid with a higher viscosity. Okay, so now you've got the upward force, drag plus upthrust, becoming eventually equal to the weight. Yeah, and when the drag force increases, a vertical force becomes balanced eventually, and when they become equal, the balanced situation is when terminal speed is reached. Yeah, in other words, the forces are balanced, means you must be moving at constant speed. So constant speed is attained, and that's what we mean by terminal velocity. And the terminal speed will obviously be lower in a liquid which is more viscous. So these are my bullet points, and you can look at the mark scheme to see where they give the marks. So I've made 4, 5, 6, 7, 8 logical points. This is the first part that we went through. And here is the content. So they're saying initially there's a downward resultant force, yeah, on either ball bearing, or the weight is greater than the upthrust, because there is a bit of upthrust. The ball bearing therefore accelerates downwards. I think I've got all so far 3 marks. The viscous drag force increases with speed. I said that. The viscous drag force at any given velocity is greater in the more viscous fluid. Yes. So I've said that too. Eventually resultant forces become 0 when the forces are balanced. So weight will become equal to upthrust plus drag. I definitely said that. And in the higher viscosity fluid, the terminal velocity will be lower. Yeah, because it'll be at a lower speed. It will be able to get the force large enough. F equals 6 pi constant, R constant, eta greater. So if eta is greater and you're balancing the same weight and the upthrust the same, the velocity will go down if eta has gone up. Hope that makes sense. And then they'll give you 4 marks for this content that I've written down, and then they'll look at your reasoning and they can give you 2 marks for the structure of your writing. Yeah, so here it says answer shows a coherent and logical structure with the linkages and fully sustained lines of reasoning throughout your written answer. So any confusion, you'll just drop 1 mark. Okay, so I hope that makes sense. Part C, it then says the ball bearing fell at terminal velocity through a liquid. Yeah, so terminal velocity can be determined because it fell 0.75 meters in a time of 3.4 seconds. Yeah, so you just work out the velocity, and that gives you a value of 0.22 meters per second to 2 significant figures. They've then given you the viscosity and they've given you the radius, and you've got to make sure they're in the correct units, so change it to meters. The viscosity is in the correct units already. They want you to calculate the viscous drag. All you've got to do is put the numbers in. 6 pi we know, R, that's eta, sorry, this is 1.8 is eta, and this is the radius, and that is the velocity. So all you do is put the numbers in, and again 2 significant figures seems to be the order of the day that you should put in there. Okay, 2 significant figures, because the data provided is 2 significant figures. This is the last part of section A, the last part of this question 13. A student considers what would happen if the temperature of the liquid increases. Well, if the temperature goes up, the viscosity decreases. You need to know that. The student writes the following statement: when the temperature increases, the viscosity decreases. Yeah, I agree with that, so I've given that bit a tick. But therefore he says when the ball bearing is falling at terminal velocity, the viscous drag will be less. Well, I think he's wrong over there, and I'm going to explain why. Okay, the first sentence is correct. As temperature increases, viscosity decreases. But at terminal speed, vertical forces are still balanced. Yeah, otherwise they won't be at terminal speed. And weight equals drag plus upthrust. And since the weight and the upthrust aren't affected, yeah, because obviously the ball bearing hasn't changed. So therefore the volume is the same, so the upthrust is the same. And The weight obviously hasn't changed because it's the same ball bearing. So it's the weight and the upthrust are not affected by the change in temperature. Only the viscosity is. So drag force will also be the same. So student is incorrect in the second part of the statement, because if eta goes up, the velocity will increase to keep the drag force the same to be able to reach terminal velocity. It has to do that to reach this situation of this force diagram. Okay, and there's your 14 marks for this last question in section A. So 56 marks for this section, and then here's the mark scheme. You can stop the video and look at it at your leisure. And now we're going to go to section B. I forgot to enlarge the screen, so apologies for the question 13. It's just the linear exam. They put the question paper portrait and they put the mark scheme landscape. So the iPad wants to show the full width of the landscape, and I forgot to expand it. So now they want you to, section B is more about application of physics, okay, and comprehension. Read the extract and answer the following questions. Scientists have observed small dust particles jumping above the moon's surface, okay. Small particles on the surface of the moon acquire a charge due to the photoelectric effect. So remember what the photoelectric effect is? Light coming in, yeah, so light coming in of a certain frequency hits something, yeah, so this will be a photon of a certain frequency. It's meant to be a packet of energy that I've drawn. Not very good. So let's try and draw that again. So imagine you got some orange light coming in. Yeah, this much energy is coming in, and is caused by ultraviolet radiation. So I should have really drawn it in purple. So imagine this is purple. Let's see if I can get purple. There you go. I'm going to use this one. Okay, let's see if I can do that. So the photon should be really a violet color, this UV energy. Okay, so I'm going to use this purple because I like purple. Okay, so by the instant ultraviolet radiation from the sun, electrostatic forces between charged dust particle cause these particles to move. Okay, so there's going to be electrostatic charges between them. So if they've lost electrons, they should become positive. It is believed that this is a mechanism by which dust particles can be transported across vast regions of the moon. Okay, so I don't know about that, but anyway, let's see what the physics is. Explain how the incident UV radiation causes the dust particles to become charged by what is known as the photoelectric effect. Okay, so electrons absorb this ultraviolet energy, yeah? Each ultraviolet photon, one photon, can be given to one electron, so the energy is in packets. You either take it or leave it, yeah? So the HF energy, yeah, violet color. Some electrons are then released from the dust particle because they gain this energy from the photons, and leaving the dust particles with a deficit of electrons, which means that they are now have a net positive charge if you lose electrons. So it's electron transfer. Electron loss leads to positive outcomes. Okay? I hope that makes sense. I do like this purple color. All right. It then says, going back to my yellow, the angle at which the ultraviolet radiation is incident on the moon varies across its surface as shown. So imagine this is the equator. It then hits the surface perpendicularly. So that means at 90 degrees, so you're going to get maximum intensity at the moon's equivalent of the equator. But if you get lower intensity, the higher, closer to the North Pole you are, if you like. If the moon has a North Pole, you imagine it, because this, you can see it's at an angle. So the intensity will be spread out, just like if you shine a torch directly on a piece of paper at 90 degrees to it, the area of the light will be smaller. Whereas if you tilt the paper at a large angle, then the same torch, the light will be spread out in a larger area. Therefore, the intensity of the light is spread out and it's less energetic per meter squared. So it says the number of dust particles per unit area that become charged is greatest where the ultraviolet radiation is instant at 90 degrees, which is what I was explaining. You got to explain what I just explained, because it says explain why. At 90 degrees, the photons instant are spread over the smallest possible surface area, or a smaller surface area, than angles to the surface of less than 90, depending on how you measure the angle. See the theta in my diagram, okay? See here I've drawn a little theta for you. All right, so the intensity of the UV photons is higher at 90 degrees, What does that mean? It means per square centimeter or per square meter, more photons are hitting the surface per unit area. Hitting the surface per second also. So more dust particles in that region, talking about when it's a 90 degree instant angle, can release electrons, because more of them are going to get the energy from these high energy ultraviolet photons, i.e. more electrons are released by the UV light at 90 degrees to the surface than near the North Pole of the moon. Okay, that's exactly the same reason why it's warmer at the equator than the North Pole, because the intensity of sunlight is much greater. Okay, here they're giving you the work functions of some minerals that have been found on the surface of the moon. Okay, now remember, the work functions when we did photoelectric effect are usually with metals, so they're just adapting it for this moon question. Ultraviolet radiation with a frequency of 2.0 times 10 to the 15 hertz is instant on a sample of one of these minerals, and electrons are emitted by means of this photoelectric effect. So the photon energy comes in, it must be at least equal to the work function, and any excess will give you the kinetic energy. Now, the work function is the minimum energy required to get the electron to the surface of the mineral or the metal. And frequency energy can be worked out using Planck's constant times the frequency which is given to us. So we kind of know the energy, but they want to know the released electrons have a maximum kinetic energy of 4 electron volts. So they're giving you in electron volts, okay, rather than joules. So deduce the mineral from which the photoelectron is released, okay? So how do you do this? So since we know HF equals the equation I gave you, HF plus the maximum kinetic energy, and they're telling us the maximum kinetic energy is 4 electron volts, you can convert that to joules, yes? So you can compare it with the photon energy in joules. Okay, that's what I would do. Alternatively, you could convert the photon energy into electron volts as an alternative method. It would be that. Okay, I'm using the yellow method. So to find work function, we know the photon energy it looks like I've done it in electron volts. So I'm keeping it in electron volts, which makes sense because the answers are in electron volts. So I'm confusing you a little bit. And then you take away the 4.0 because that is the maximum kinetic energy. So that's the 4.0. And we want to find phi, so we made phi the subject of the equation. So I have done the blue method, not the yellow method now. So I'm changing the photon energy which was given above here. I'm dividing that by 1.69 times 10 to the minus 19, which is the electron charge, and that's how you change joules into electron volts. Once you do that, put the numbers in a calculator and then take away 4, you will be left with 4.3 electron volts. So that's equal to the work function of the first mineral called ilmenite. Yes? So therefore you can show that you've deduced that the mineral is ilmenite. You've deduced the mineral. Yeah? And that takes us to the mark scheme for 14A, B, and C. I'll let you pause the video if you want to take a longer look at it. And here is part D. So this is a long question. And these are the end of the papers for the linear are long questions. Okay? In part D, it says the motion of a charged dust particle is influenced by other nearby charged dust particles as well as the moon's gravity. Yeah, because obviously every particle has mass, and because they're charged, they also feel the electrostatic force. The lack of an atmosphere on the moon means that the dust particles don't have any resistive forces. Okay, so this is just giving you some extra information. A particular dust particle experiences an electrostatic force of 8.2 times 10 to the minus 17 newtons that is perpendicular to the gravity. Well, gravity is obviously downwards, so it's going to be at right angles to downwards, so it would be horizontal. The magnitude of the resultant force is also given to you as 8.7 times 10 to the minus 17. So what you have to do, you have to calculate the magnitude and direction of the acceleration of the particle. Yeah? So if we know all the forces, yeah, because they're vectors, then you also know F equals ma, and they want us to work out A. So they want us to work out A, the acceleration of the particle. They want the magnitude and direction of the acceleration, not the force. So what have they given us? They've given us the moon's gravity. The gravitational field strength on the moon is 1.6 rather than 10 on Earth. They've given us weight of 3.0 times 10 to the minus 17. So you can now work out the mass because you know that mass is W over G. So all you've got to do is put these two values in to W over G, and you'll get that the mass is tiny, 1.9 times 10 to the minus 17 kilograms. Okay? So the other thing we know, this is the dust particle there. The gravitational force is pulling it downwards, and the electrostatic force, which they gave us, is pulling it sideways, so it could be to the right. And the resultant force must be the addition of these two forces. So you can just add these as vector forces, yeah? And I'm going to draw it in blue. This will be the vector addition of the electrostatic force plus the gravitational force, which is the equivalent, will add up to this resultant force. So we kind of know if it will be to the theta to the horizontal, yes? Theta downward from the horizontal, if you like. So we know everything. We know all sides of this right angle triangle. All we need to do is to do some algebra, but before, to work out theta. So tan theta, for example, would be opposite, which would be the gravity, yeah, divided by 8.2. And you'll notice that the 10 to the minus 17s cancel all over the place. So that'll give you the angle to the horizontal, downwards from the horizontal, of 20.1 degrees. Okay? And that's all you can say about the angle, because they haven't told us if the horizontal motion is to the right or the left. I'm just assuming it's to the right. And then you can use Newton's second law to use acceleration as force, resultant force you've got to use, yeah, which they gave us here, 8.7 times 10 to the minus 17, divided by the mass, which you worked out. So you put the mass in there, and you put that in there, and again the 10 to the minus 17s cancel out, and you get an acceleration of 4.6 meters per second squared along the angle that we just worked out. And you put the values in here, and make sure you express the angle correctly in terms of direction. Okay? And that's the end of question 14. There's the mark scheme for it. Yeah. So all they want is theta is 20 degrees to the horizontal downwards. Okay? Because it could be theta to 20 degrees to the horizontal upwards. Okay? And it's not upwards. It has to go down because of gravity. All right, so the last question is 15. A rain sensor is mounted on the inside of a car windscreen. When the rain sensor detects raindrops on the windscreen, a motor is automatically switched on. Yeah? So that's clever. The rain sensor consists of a series of infrared emitters and detectors. Infrared rays are emitted from a sensor, travel through the glass windscreen, and are incident on the outside surface, which will be air. Yeah? Unless it's wet. So when it's dry, it will behave differently because it's going to air. When it's wet, there'll be a raindrop, and it will change the refraction ability. The array is incident on the boundary between the glass and a raindrop, as shown. Yes? So normally the outside of the car will be air, but where there's a raindrop, there'll be water. Yes? So you've got, this is the glass. This is the thickness of the glass. Yes? And of course, inside the car is also air. And here is your rain sensor. Yeah? So remember they said it had infrared emitters and detectors. All right. The angle of incident is 45 degrees. So this angle here is 45 degrees. Okay? Determine what happens to the ray at this boundary when there's a raindrop. So the refractive index of glass is 1.5 and of water is 1.3. So you can use this equation, yeah, for glass to raindrop, which is water. Okay, so we know N1, we know N2, we know sine theta 1, we do not know sine theta 2. So all you've got to do is work out the angle on the other side of the glass to the dotted line, which is the normal. Okay, and when you put the numbers in, you'll show that the refracted angle is 55 degrees. That means it refracts through into the raindrop. Okay, if the raindrop wasn't there, it would totally internally reflect, because I know that the critical angle, if it was air, would be 42 degrees for air. But for water, it'll be more like 60 degrees. Yeah? And that was a point of confusion for some of my students. So it's going to refract. It's going to be refracting at 55 degrees, as shown in red. Yeah? So I've drawn the refracted ray. What happens to the ray at this boundary? It refracts. Okay? But when it's not raining, the instant ray at 45 degrees would totally internally reflect, because it would be air, and the critical angle from glass to air is 42 degrees. And if you work it out for glass to water, I think it's about 60 degrees. So critical angle for water from glass is approximately, let's just say it's about 60 degrees from glass to water. So remember, critical angles depends on what is on each side, or what a refractive index is, the incident angle is in, and the refracted rays are going through. Okay, part B, it says students model a simple infrared detector using a light-dependent resistor. Yes, LDR, in series with a variable resistor. She connects the motor in parallel with an LDR. So what are we talking about here? Electricity. So this paper 2 is mainly waves and materials, and here you've got an application from electricity, which is using potential dividers, or a potential divider. Now, a potential divider is when the two resistances divide the potential that's available, which is the battery potential, between them, according to their resistance. The intensity of light incident on the LDR increases, and that means the resistance of the LDR will decrease. Okay? They want to know what happens to the speed of the motor. Okay? Well, it depends on what will happen to the voltage. Your answer should include a reference to conduction electrons. Okay? You don't actually need to know about conduction electrons to know what's happening to the motor, but you have to do that to get one of the marks. It's 4 marks they're looking for. So the resistance of the LDR will decrease because light's increased, okay? And the reason is that the resistance decreases is that it decreases with light intensity because the energy of the photons coming in this particular material that the LDR is made of, it actually liberates, it energizes the electrons rather than liberates. The number of conduction electrons increases due to the energy of the light. Yeah? And therefore, in the equation I equals NAVE, N increases. So you have more conduction electrons, and that's why it's less resistant. Yeah? So if the resistance of the LDR decreases due to the more conduction electrons, then the voltage across the LDR will also decrease. Because remember that the voltage of the supply, Vs, is shared between the two resistances, and if the LDR resistance has gone down, it's going to get a smaller share of the total resistance, therefore the total voltage. Okay? So the speed of the motor will decrease because its voltage is in parallel with the LDR, and the voltage of the LDR will decrease. And that's how you get the 4 marks. Yeah? And the reason the voltage of the LDR decreases is because the ratio of the resistances now is less for the LDR, and therefore as a resistance is lower, so it will get a smaller share of the battery's potential difference. Okay, there is parts 15A and B. And there you see the critical angle for glass to water, yeah, is 60 degrees. And here's the 4 marks that I was explaining just now to you. And here is the final part of this run through. The power supply consists of 1.5 volts cells joined together. They want you to work out how many there are. The student set the resistance of the resistor to 270 ohms. So that's a variable resistor, so I put RVR, and measured the potential difference across the motor as 5 volts. Okay? In this situation, the resistance of the LDR is given as 193 ohms. So we know the total resistance, we know the resistance of each one, and we know that the output of the voltmeter is 5 volts. Okay? Now it says the motor had a very high resistance. In other words, you do not have to worry about the fact that it is in parallel with the LDR. In other words, they're making it easier for you. Deduce the number of cells that were in the battery. So that we've got to find out the supply of the voltage, yeah, and then see how many 1.5 volts that is. So the total resistance we know is 463 ohms. And we know that the voltage of the LDR is 5 volts, yes, given to us in the question. So we know this value, we know our LDR, and we know the total resistance. The only thing we don't know is the voltage of the supply. So change the equation around, yeah. Make voltage as a supply the subject, and you get the numbers 463 divided by 193, multiplied by 5 gives you 12 volts to 3 significant figures. That means you need 8 1.5 volt cells to make 12 volts. And that's how you get the final 3 marks for this AS Core Physics 2 paper, which totals for 80 marks. So I hope you found that useful. Don't forget to like it, share it, and let people know that I'm starting to do linear as well as international A-level. Your help and appreciation is greatly requested and appreciated. So thanks for watching. Catch you in the next video. Bye for now.